Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is just go through some quick kind of conceptual examples of calculating potential difference here. So what we're looking at, we've got this region in space here. I got three sets of coordinates here defined by some coordinate system. We've got point A here is at the point 0, 0. Point B is at the point 3, 0. Point C is at the point 3, 2.5, where these distances are in meters. In this region in space here, we're going to assume a uniform electric field of 100 Newton per Coulomb to the right, or in other words, in the plus I direction. And I'm just going to walk through some calculations here and talk about the potential differences between A and B, A and C, and B and C. So let's start with just a quick review of potential difference and how it relates to electric fields. And I'm going to do this in an algebraic sense. I'm going to avoid the math. Basically, potential difference is field strength times distance. There's a couple little things we got to consider here, some details that go with this. When you calculate potential difference, the electric field and the distance have to be parallel to one another. And also, there's a positive or negative thing to consider. When you look at equations of the book, they usually will have maybe something like a minus sign here. I'm just going to do this. I'm going to say the magnitude of the potential difference is E times D. And I like to think about this conceptually. I always make people memorize this sentence. Electric potential always decreases in the direction of the field. So in my example here, anytime we go to the right, we're going to be moving towards lower potential. And anytime we go to the left, we're going to be moving towards higher potential. So anytime we're moving to the right, I'll just call the potential difference negative. Anytime we're moving to the left, I'm going to call the potential difference positive. So here we go. Working the calculations now. Now from A to B, the distance between them, we're going from the point 0, 0 to 3, 0. So the distance between them is 3. So the potential difference between A and B, we're going to have the field strength, 100 Newton per Coulomb, times a distance of 3 meters. And out comes 300 Newton meter, which is a joule, 300 joule per Coulomb. Because we are dropping in potential, that potential difference is negative, meaning that potential B is 300 joule per Coulomb lower than potential A. So potential difference between A and B, minus 300 joule per Coulomb, which is, by the way, a volt. So I'll just go ahead and just put minus 300 volts. So that's what a joule per Coulomb is. All right, now potential difference between A and C. So when we're talking about from A to C here, now we're talking about a two-dimensional kind of problem here. So what I'm going to do is chat about this in the language of vectors. So imagine that we have a displacement vector that points from A to C. And I might give that vector name like R. If I think about that vector in terms of components, it's 3 meters to the right and 2.5 meters high. So we're going to have got that in the wrong place. So I could write this in unit vector form, 3i plus 2.5j, where these distances are in meters. Now, when you're calculating potential difference, again, the electric field and the distance have to be parallel. Now, the electric field vector points to the right. So the only distance that matters here when we go from A to B is the 3 meters. The distance from the 0.30 to the 2.5, this vertical distance, the 2.5, doesn't matter at all. In fact, remember, obviously my video is about equipotentials. Because the electric field is to the right, this line is actually an equipotential. So when we calculate the potential difference between A and C, still only the 3 meters is the distance that matters. Whoops. So the potential difference between them is still 100 Newton per Coulomb times, again, 3 meters. The 2.5 doesn't matter because that displacement makes a right angle to the electric field. And again, that's a drop in potential still because C is downstream, so to speak, in the electric field. So we're going to get, again, minus 300 volts. Or another way to say that, the potential difference between A and C is 300 volts with A at the higher potential. All right, between B and C, now I've already discussed this. The displacement between B and C is just a vertical displacement. You'd have to go this way. The electric field points this way everywhere. maybe something like this. Anyway, what I'm talking about is this vector here is good all along this path, so there is no component of the electric field in the direction of displacement, so the potential difference between B and C, 0. So again, I just wanted this to be kind of a conceptual video about calculating potential differences. So again, A is at the highest potential, B and C are 300 volts lower. Now again, these are potential differences. The actual value of the potential can't really be determined until one defines a datum. And again, it's fairly an arbitrary thing, and I'd like to go through some examples to kind of illustrate this. If I wanted to, I could measure my potential equals 0 here. Then we would say the potential at A is 0. The potential at B and C would then be minus 300 volts. However, we could also put our datum here and say that potentials B and C are 0, in fact, anywhere along this line or surface. And then A would be at a potential of positive 300 volts. Or if I wanted to, we could put a datum right in between them. In which case A would now be at plus 150, B would now be at minus 150. The only thing that ever matters in equations are differences in potential, changes in potential. So anyway, just wanted this to be a kind of simple conceptual video about calculating potential difference with a given electric field. I hope I've accomplished that. Have a great day.